Hello, and welcome to Lecture 2 of the Electric Potential Unit in Phys 1201. In this lecture, we're going to look at how we produce electric potentials, or more to the point, potential differences, which we also call voltages. And then we're going to start seeing how we calculate electric potentials in the simplest case, which is a parallel plate capacitor. The first thing to realize is that you don't need any high-tech setup to produce a potential difference, a delta V. We also call it a voltage, remember. So just a glass rod and vinyl sheet, like we saw earlier in the course, will work. Rub them together, and some charge transfers. Remember, these are complicated insulators being rubbed together. You get some molecular ions transferred. Who knows what really happens? I'm just going to say some negative charge went over onto the vinyl sheet. Now we pull them apart, and I'll just point out, remember that this is only charged because it lost negative charge over to here, and so our total charge is still 0. We haven't made any charge, we've just shuffled it around. And now, don't think so much about the rod and the sheet. We're not really interested in them. They're source charges, and we're thinking of how they affect things around them. So here are 2 points in space in between them. And think about what happens if you put a positive charge at A. Well, it's going to be repelled from this rod and attracted to this vinyl sheet, and so we know there's an electrical force on it to the right. That tells us the E field is to the right, but I don't want to talk about the E field. I want to talk about the potential. If we release it from here, then it's going to accelerate to the right, and eventually it may pass through B, by which point it'll be going at some speed. So it's just gained kinetic energy. It must have lost electrical potential energy. And since the potential is just the potential energy over our probe charge, that tells us that point A here is a place where V is high, and point B is a place where the potential is low. And this is just another example of a standard rule that potential is high near positive charges, low near negative charges. But also note that that means V is changing through here. We have a change in potential between these two objects. And so all it takes to make a voltage, a potential difference, is that you separate charge. Now that we know that charge separation gives us a voltage, the question becomes, how do we produce charge separation in a convenient way? And there are lots of ways of doing it, but one of the most convenient turns out to be to use chemistry. And this is what goes on in a battery. Now, batteries are actually very complicated, and there are so many different types of batteries that almost anything I told you about batteries would only apply to some of them. But here's a basic thumbnail sketch of how batteries work. You have 2 electrodes made usually out of different materials, and they're immersed in some sort of solution. And there's a chemical reaction that goes on the surface of one electrode that results in positive ions coming off of the electrode and entering the solution. And then you have some other reaction on the other electrode that's resulting in negative ions coming off of the electrode and entering the solution. So with these positive ions coming off of this electrode, it's left negatively charged. And similarly, this one over here ends up positively charged. There, we've got our charge separation, and so there will be a potential difference. And in fact, what happens is that eventually there's enough charge packed onto each of these electrodes that for the reaction to continue, we'd need to be packing more on, and that takes energy. And it'll reach the point where the reaction doesn't provide enough energy to pack any more charge onto those electrodes, and at that point the reaction stops and we get a fixed potential difference. Now, if you ever connect the one electrode to the other, charge will flow, and the reaction starts up again, and it goes at just the right rate to maintain that delta V. So this is the convenient thing about a battery. It's a source of a constant potential difference. Now, that is something that a lot of people have a misconception about. A lot of people think of a battery as a source of current or as a source of charge. It is no such thing. It's a source of potential difference. There are many situations where you can hook a battery up to some device and no current flows, but the battery is producing its fixed potential difference. And similarly, we haven't made any charge here. We've just separated charge. So a battery is also not a source of charge. Now, humans made out of batteries aren't the only ones to have ever figured this out. Charge separation using chemistry goes on all the time in cells. And so, for example, at cell membranes, there are these things called ion channels, which cells use to pump different ions across their membranes to set up a potential difference across the membrane. Now that we know about batteries, let's think about what happens when we connect one up with a capacitor. Remember, this is just a cartoon picture. The plates should be very close together, not like I've drawn them. So, this battery is producing a potential difference, and that's going to do something to the plates. And I want to point out that there's nothing special about the battery. We could connect these plates up to any source of potential difference, like our glass rod and vinyl sheet, and that's going to do basically the same thing. But batteries are a lot easier to think about than these. In many ways, they're simpler, so let's stick with the battery. Well, electrons are going to be pulled off of this plate towards the negative terminal of the battery. And similarly, electrons are going to be pushed out of the negative terminal of the battery onto this plate. And so we're going to get a buildup of positive charge on one plate and negative charge on the other. And notice that all this negative charge is electrons arriving, and they came from this plate. So we're guaranteed that these charges are of equal magnitude. Well, this is the picture we had of what happens in a capacitor when we discussed them earlier in the course. So there's our charge separation. We have a potential difference. And notice that the real source of the potential difference here wasn't the capacitor. It was the battery. Basically, what the capacitor is doing is it's taking those charges separated by the battery and putting them very close together. Before we set out to calculate any potentials, here's one thing that's useful to know. Where is potential equal to zero? Remember that potential is defined in terms of the electric potential energy. So I could give the answer that V is zero wherever the potential energy is zero. That might not strike you as a really useful answer, though, because it just begs the question, where is the potential energy zero? But actually, we already know the answer to that question because we talked about it back in Phys 1101. Think about, as usual, throwing a ball up into the air. You know, just as it leaves your hand, it has a lot of kinetic energy that converts into gravitational potential energy and back into kinetic energy. And I've drawn it this way. I know that the potential energy is zero here because of where I put my axes. But of course, the universe doesn't care where I put my axes. The behavior of the ball will not pay any attention to how I define my axes. And so shifting my axes is perfectly all right. We'll get all the same answers. All that's happened is I've redefined where the potential energy is zero. So the general rule is any potential energy is zero wherever you say it is. And so that means that potential is zero wherever you want it to be, and you'll usually choose based on convenience. Let's now talk about how to calculate a potential. So the simplest case turns out to be a parallel plate capacitor. And so here it is. I've defined the charges, we know the plate area, and let's say the distance between the plates is d. And furthermore, we know I'm allowed to just arbitrarily say I want potential to be zero here on this plate. So I've set V equals 0 where X equals 0. That's going to be convenient. And the reason the parallel plate capacitor turns out to be easy is that we know that the E field inside the parallel plate capacitor is constant everywhere. And so we know it's Q over epsilon naught A. And that tells us that the force on any charge we put in here will be constant. Well, I want to think about a negative charge. So here's a negative charge that we're starting over near this plate. And we know it's going to accelerate. It's going to be pushed away from that plate and attracted to this one. It's going to wind up over here. And by the time it gets here, it's going to be moving to the right at some speed. And so now let's think about it. It loses potential energy and gains kinetic energy as it goes. We know that the change in the potential energy is just the negative work done by the electrical force. And that means it's the negative magnitude of the electrical force times the distance traveled, because this is a constant force. Well, how do we get that electrical force? I'm going to say I know that this delta UE must be negative, right? This charge must lose potential energy as it goes this way. And so here's the negative we need. I can just think about magnitudes here, not worry about signs in here. That electrical force, then, its magnitude is just going to be QE, right? We can always do that. We can get a force on a charge if we know the electrical field. So here we go. We've got negative QE delta x, but delta x is just d. That's the distance traveled. And so our delta UE is negative Q, capital Q over epsilon naught A d. But look what we can do now. Our delta V has to be our delta U over our probe charge, which is negative Q. Negative Q. And so if we just divide this by negative Q, it's going to take this negative Q out, and we just end up with big Q over epsilon naught A d. So look at what we have now. We know that the potential on this plate is 0 because we say so. And now we know the potential difference. It has to get higher as we move towards the positive plate, right? Potential is always high near positives and low near negatives. And this one came out to be Q over epsilon naught A d. But remember, that's arbitrary where 0 was. I could just as well have called this one 0, and this one would turn out then to be negative Q over epsilon naught A d. It's the delta V that we actually know. We don't have a choice there. Let's now think about the potential everywhere else inside the capacitor. So think about now the charge having left this plate, and we're going to think of its potential energy as it passes through some other location A, which is some distance x from this plate. So if you just follow the same reasoning, all you're doing is replacing this d with x, and this now gives you V, the potential, as a function of x is going to be just this expression exactly, but with the d replaced with x. And think about what that looks like. If we graph that, we know that we set the potential to be 0 at x equals 0. And it rises, and we know that out here at d, the potential is Q over epsilon naught A d. So we know that much. But then in between, it's just this function. And look, it's an x to the power of 1, so that's a linear function. And so our potential as a function of position inside a parallel plate capacitor is just a straight line with a slope there. The slope is Q over epsilon naught A. Oh, hey, look, that just happens to be the electric field strength.